Yeah, so this is just the definition of the Laplace transform.
Okay.
So now I'm going to write this down exactly the way it was written in the paper, right? And it says the Laplace transform of f prime of s. Where is the prime? What does the prime apply to? Does it apply to the Fourier transform or does it apply to f?
F.
F. So this is the Fourier transform of f prime of s. Okay, so it's not the way I had it written. It's like you have to take the derivative of f prime. Now we're still going to use integration by parts, but the formula is going to be slightly different. Okay, so this was my mistake. I'm sorry I wasted 5 minutes talking about it. It's still illustrative, I think. So what is the the Fourier transform of f prime? I'm sorry, I keep saying Laplace. It's the next thing we're going to do is the Laplace transform. So the Fourier transform of f prime is the integral from minus infinity to infinity of f prime of t e to the minus 2 pi I st. Okay, so now this actually should be, I was like, well, how the hell did I write a question that was so hard? I didn't mean to. Now what we're trying to show, this is the left-hand side. All of this is the left-hand side. This is just applying the Fourier transform formula to f prime. On the right-hand side, we're going to, what are we trying to show? We're trying to show that it's equal to 2 pi I s times the integral of f e to the minus 2 pi I st dt. Now I'm going to ask you the same question I asked before. How could I possibly show that these two things are equal? This has an f prime in it, and this has an f in it. How am I going to do that? I have to Go ahead.
How did you yank out the 2 pi is from like the FFT?
Because the actual statement of the problem, is, so this would be, I think, make this easier. The problem says this. If I can get my pen working. What the? Show that the Fourier transform of f prime of s is equal to 2 pi I s integral, times the Fourier transform of f. It says show it.
Okay.
So it's not the case where we knew that coming in. What we're doing is we're saying, okay, well, that formula is easy because that's this integral right here. And this formula is just the Laplace transform of f. And the 2 pi is goes right here.
Okay, that makes sense.
Okay. So I don't actually know that these are equal yet. I'm just manipulating the two sides separately from each other just by writing the integrals in. Okay. So now I have the same question before and it's got the same answer. I've got one side of this thing that has an f prime inside of it, and the other side has an f, and I'm somehow supposed to show that these things are equal. What could I do? If only I knew what the integral of f prime was.
Isn't that just f?
It is.
Ooh.
So what technique should I use?
Integration?
By?
Parts?
Yep. What should I let u be?
So I guess you let u be the e to the negative 2 pi thing, and then the dv would be the f prime.
Yeah. And the reason that you do that is because then du is minus, remember that these are all with respect to t, right? Minus 2 pi is. Oh, that looks nice. That looks like almost like something we need. And then over here, the integral of f prime is f. So this right here is u times v, and this right here is the integral of v du. So when you write down uv minus the integral of v du, you get, well, what is uv? F e to the minus 2 pi I st, evaluated from minus infinity to infinity, plus 2 pi is times the integral of f e to the minus 2 pi I st. Now the next question is, what's that? This thing right here. What is that equal to? Because this thing right here is exactly what I wanted. It's this integral right here, right? Now I've got that. This finally is in the problem because I've got it right here. So I integrated the left-hand side by parts, and I got the integral I wanted, but I've got this extra piece.
I mean, I guess that has to be 0, right?
Just why? Why does it have
the problem? They're both equal, but I don't know why that specifically would be.
Okay. So what are the conditions that we have on f? That's the first thing. What hypotheses do we get about the integral of f, or the behavior of f? It told us that the limit as t goes to infinity of f is 0. Right? And so what that's going to do is that's going to force that should force this integral to turn into nothing. As long as I didn't write a typo in the problem somewhere. Let's see. Double check. Because that limit is going to drive... Hold on a second, guys. There's just too many things going on in this class. You guys have said pretty much the same thing. It's definitely too much going on in here. Yeah, I meant to ask you, how are you feeling about taking a class that is 4 classes shoved into 2?
Hard.
Little dense with material. Yeah. So this is supposed to be a limit as t goes to plus and minus infinity. Not just plus infinity, which I'll add. But what that means is that f kind of has the behavior that it's asymptotic to 0 as you go out.
We should just remember that.
I'm going to put it in the I'll adjust the homework assignment so that it's written there.
Okay, for sure.
But to get to this, to even get to this point though, you know that something must happen because this has to be 0, because this is the integral that we're trying to show is true. This is the way all these formula type questions go, is that you basically just apply the integral and then stuff happens, and then you should just be able to identify, like when I'm looking at it, I can see that this is the Fourier transform of f. Right? And then out front of it, it's got a 2 pi is. And if you don't see it, then you could just write down what the Fourier transform of f is so that you've got it on the page for you to look at. So it must be the case that on the left-hand side, you know, at this point, what we've shown is the left-hand side is the Fourier transform of f prime of s. And on the right-hand side, we have this f e to the minus 2 pi ist evaluated from minus infinity to infinity, plus 2 pi is times the Fourier transform of f. And what we were trying to show is that these two things are equal, that this and this are equal. So the only possibility is that this must be equal to 0. And now your next question is, why is that equal to 0? So this is just actually L'Hopital's rule, right? Because you've got something that is, when you put the minus infinity to infinity, and what's going to happen is this thing is going to be equal to 0 on the left and 0 on the right, and that turns into a 0 over 0. So it just cancels.
I kind of have a question on that. So it looks like you determined it to be 0 because we were given the condition about the limit. As t approaches to infinity, f is 0. But wouldn't you say something about e, since we're substituting the infinities for t in this case? So you would like say something about e to the infinity, like minus e to the negative infinity?
Yeah, so when you put in positive infinity, what you end up with here is f. It doesn't really matter what f does at infinity, right? Because e to the minus infinity is nothing.
Mm-hmm.
When you put in, is this question just written incorrectly? No. F is bounded. F is... Okay. So what this is going to follow from, so you're right. So you're asking, do I need to say something about the interaction of f with e,
Yeah.
right? So what I would do in this situation is, I've already told you, I'm supposed to have told you that the limit as t goes to plus and minus infinity of f is equal to 0. But we can actually reconstruct what the conditions on f have to be in order to make this actually explicitly true. If this formula is going to hold, this is going to have to be 0. What conditions would we need to have that happen? Well, it certainly has to be the case that f dies off to the asymptotes, right, as we go out, because otherwise f has infinite area and the whole thing is going to blow up, right? So we need this condition. This is necessary. What else do we need? we also need the case that the integral from minus infinity to of f dt is less than or equal to infinity. That better be bounded. So I can't have anything happen where the function like expands out, in huge pieces or oscillates wildly or whatever as you get out towards infinity. So there's things we need to say about like f to make this integral be finite. But what do we know about f? We know that f is continuous, and we know it has a continuous derivative. So if f is continuous and Jesus, this is hard to organize my thoughts about. One of the things that we showed earlier in the class was that when you had f in C1, remember that f to be in C1 means that f and f hat are continuous, or f and f prime are continuous. And we've also assumed that these transforms exist. This formula doesn't make any sense if the transforms don't exist, right? And we've also assumed that transforms exist. And what else do we need? We need the fact that the area under f is finite. Because if the area underneath f isn't finite, then it wouldn't even make any sense to write the integral down to begin with, right? I mean, you would never write down an integral from minus infinity to infinity or a Fourier transform of a function for which it was the case that this area was not, why do I say less than or equal to infinity? Less than infinity. All of these things need to be true. And so I've pulled away from talking about these formulas and now I'm talking about technical conditions. But the basic idea is that when you're thinking of an f that this is applying to, you should be thinking, because of this condition and this condition and this condition and this condition, you should be thinking about a function that behaves like this. The model function I want you to have in mind is the functions that we've been talking about, like the triangle function, for example, where it comes in, come on, pen, and it bumps up with finite area and then goes back down to being 0. You don't do Fourier transforms of things that don't act like this. Okay, you can't. Doesn't make any sense. The other thing that you need to have happen is that if f is going to have like area that's finite, if it does have asymptotic behavior, then you can only do Fourier transforms of functions like Gaussians, right? So a Gaussian comes in and goes up, and it's non-zero forever, but it goes to 0 so quickly that the area from minus infinity to infinity is nothing. Like that's a hard condition. So the area under this curve is 1, right? So like e to the minus pi x squared, for example. That's a function you can take a Fourier transform of because the area underneath it is controlled by the fact that it's asymptotic to 0 so quickly. So Fourier transforms, the model function that I want you to have in mind is either the rectangle function, which comes in, bumps up, has a finite box, and then goes back away again, where we're always cutting the integral down to some kind of box. Or it's so quickly asymptotic to 0 that it's basically exponential in nature. And that's what's going to control this interaction right here. The fact that you have f mixed with this complex exponential. Okay.
So should we just know that when you have an f and that e to the 2 pi thing, that it's going to be so quickly going from negative infinity to negative infinity, it's just 0?
Yeah, so like basically the thing that you should have in mind is that the Fourier transforms, because they're two-sided, because it's a two-sided integral, because you have this minus infinity involved, that f has severe restrictions on, I mean, so it's not something you should just know. It's something that you should have like taken away from a conversation like this, right? That if we're going to deal with f's that have infinite area, that expand out, not infinite area, but expand out forever, that are non-zero on an infinite set, then they have to be extremely asymptotic to 0, because otherwise it doesn't make any sense to talk about their Fourier transforms at all, right?
Mm-hmm.
I mean, because the Fourier transform of f, the fact that the Fourier transform of f exists, so the very fact that the Fourier transform of f exists is enough to force it to be the case that the integral from minus infinity to infinity of, I mean, what does that mean? It means that the integral from minus infinity to f of e to the minus 2 pi I st dt, not that. What I want here is
The fe thing, fe to the negative infinity to infinity.
Yeah. Yeah, right. I mean, the fact that this exists at all means that when you take something like f and you evaluate it from how am I more clear here? I mean, look at the difference between what's happening here. So when we have the gosh, this is hard to talk about. Yes, because the Fourier transform of f exists, and the Fourier transform of f is a two-sided infinite integral, then in order for this to even make sense, because this behavior out here, as t goes to minus infinity, that thing blows up, right? For a given value of s, that thing blows up as you go to the left. So the fact that this exists and this is two-sided means that f has to be what I would call very, this is a very technical term, very here, has to be very asymptotic to 0. Or just equal to 0 outside of a finite set. Because if that doesn't happen, this can't possibly exist.
It goes like way too big or something like that?
Yeah, because the exponential part, as you crawl out towards minus infinity for a given value of s, if you let t go to negative infinity for a given value of s, it blows up as you go to the left exponentially, right?
Okay.
F has to, so like this thing, as t go, and I think this gets Teo's question as well, as t goes to minus infinity, e to the minus 2 pi I st dt, or e to the minus 2 pi st blows up. If s is positive, that blows up, right? Because that exponential looks like this. It doesn't just blow up, it blows up exponentially. That thing is just cranking away to positive infinity as you go to the left. So whatever f is doing has to counteract that of exponential order. In order for the Fourier transform to make sense at all, f has to be dying exponentially so that it counteract the fact that e is growing exponentially.
Okay.
Right? And that's actually what forces the order of f and to be exponential. Right? To the right, it's not a big deal because you have exponential growth to 0 in, as f is tending to 0 and the exponential is tending to 0 also, then they just agree and they crush to 0. So over here, there's no problem. But the fact that the Fourier transform exists is going to force f to counteract this. So I think of integration of things that are going to infinity as like fighting each other, right? So if I have an integral that looks like, let's just suppose that s is some positive value. If I have an integral that goes from minus infinity to infinity of f of t e to the minus 2 pi I st dt, and I think of it as broken into a piece from minus infinity to 0, it doesn't really matter where you make the breakpoint, but let's just think about it that way. And another piece from 0 to infinity, 2 pi I st dt. If f goes to 0 as you go to plus or minus infinity, this is okay. That's okay. F is going to 0, the exponential is going to 0. There's no convergence to check at all. That just exists. This just exists. But for this thing to exist, which is the only way the transform could make sense is if the nasty part here exists. That means that f had better be going to 0, but even more, f had better be going to 0 faster. Or we say equal to or faster than e to the 2 pi ist. Because if t is negative, this thing is charging off to positive infinity.
Okay.
Right? And so essentially what you mean is like there's faster ways to say this, but as t goes to minus infinity, you would say something like f is about equal to, well, f is O of e to the x or something. If you've seen a big O notation before, what you're saying is that as it's comparable in behavior to the exponential as you charge off to minus infinity.
Okay.
Okay, so now have I lost anybody in the technicalities here? And if I have, remember that the function to keep in mind when you're thinking about Fourier transforms is just this function. finite area on a finite interval. That those are the Fs that are the most natural objects for considering for Fourier transforms, and why we've spent so much of our time talking about functions that look like this one. Because there's real weakness in the fact that the Fourier transform is a two-sided transform. Because we have to deal with the behavior of F as it goes to positive infinity, but also negative infinity. And that puts real constraints on the behavior of F.
Thank you. You definitely answered that question.
Okay, I mean, I've over-answered it. I think I mentioned before in office hours that it made me laugh when I had students in previous classes that were complaining about one of their engineering professors. This is a different school. They were talking, they would say things like, man, I totally understood what he was talking about. And then he kept talking and he talked his way right through me understanding it and out the other side until I had no idea what was going on. So he should have just stopped talking after 5 minutes, and then, because, the next 15 just confused me. So I guess really what we're driving at here, and the point of this question is, F is highly constrained in behavior if the Fourier transform of F is to exist. And essentially what we mean by that is just that we have to be careful about the fact that we choose Fs that die off as t goes to plus and minus infinity very quickly, or just finite Fs. And that's okay in most cases because we're only ever working with finite blocks of functions in most applications. Okay, and so then the point is that because the Laplace transform of F, because the Fourier transform of F exists, then this piece up here that we were looking at all the way back up, wherever I put it, where is it? Holy crap. Oh, this right here. Okay, so the point is that because the behavior of F is so highly constrained, that's going to have to be 0. Okay, this term must be 0 because F has to die to 0 exponentially as t goes to plus or minus infinity, or the Fourier transform of F doesn't make any sense. All right. So the point of this exercise is actually specifically to deal with issues like this. Now, if I was going to ask you a question on an exam, I might just give you a specific function, right? I give you the rectangle function. That'd be pretty easy to just show the formula directly with the rectangle function. I don't even know if I would do that because that would be cruelty to ask you on a 50-minute exam to do a question like this, but that's the basic idea. So this is equal to 0 specifically because the Fourier transform of F exists. All right.
Do you think we could go over the quiz next?
The quiz. Oh yeah, which one?
Actually the last two quizzes.
Sure.
Great on.
I mean, we can talk about anything, anything that we want. So, what do you want?
Let's do the quiz that happened 2 weeks ago. I honestly the last two quizzes both I didn't do so well.
All right. So let's see. So that was, where did I put that? It's in Canvas. Quiz 3. Okay.
Quiz 3 and 4.
Yeah, I got it. I got it up right now. I just want to make sure that I guess the last thing I'll talk about here, but on the homework exercises before we move on, is that there's a reason why I'm choosing the homework exercises that I am, and that involve these technical issues, because in the classes that you guys are going to take following this one, where you're using things like the Fourier transform, knowing something about the behavior of the functions you're studying has real implications for the systems that you're trying to solve with the transform. So the technical issues might seem like they don't matter so much, right? Like, who cares? It's just like me throwing around limits of infinity. Like, this is something mathematicians care about, not engineers. But in a physical system, it actually matters a lot what you choose for the functions that you're trying to model and the conditions that exist on them, which is why in practical applications, you have to cut yourself down to families of functions that actually make sense. So it's almost backwards, right? I've got this equation and I want to use it, but I can't only use it for certain f's. So you just say, oh, well, the physical world only exists of these f's, and any other f I don't deal with, right? Any other f will be the land of mathematicians, because it's good enough for me to approximate with things, for example, that cut off at plus or minus a and then are just zero forever, right? Or that have this sort of exponential Gaussian behavior. So don't think I'm just randomly picking these exercises. I know there's technical complications in here. Now, as far as quiz 3 goes, which question? Let's do the easy one first.
Yeah, can we just do both? Because I got like a little bit of points on both, but
all right.
Both of
so
them.
d by dz of the sum from n is equal to 0 to infinity of zn over n factorial. All right, somebody tell me what to do. Here, I'll start by telling you what not to do. You are not allowed to say, here's what you are not allowed to do. You are not allowed to say that, I guess what you were trying to show is that this is equal to itself, right? Here is a circular argument. Oh, well, this is the same as saying d by dz of e to the z, which obviously is e to the z, and the power series for e to the z is this, and so you're finished, right? Because you did it. The derivative of e to the z is e to the z, so you're done.
That's definitely what I did.
So, okay. So now you can't do that, because the fact that this is true is what proves that the derivative of e to the z is e to the z. You can't just start by assuming that e to the z, the derivative of e to the z is e to the z. That's like saying, I want a magic function to exist that has this happen. So I know a lot of people in here, specifically, I know a lot of people in here did this the right way. How do you do it? What's the move? Come on, someone impress me. No?
You pull the derivative into the summation and then you like derive each term.
Yeah, so now there's actually a really straightforward way of doing it. So the way you're talking about would be, you just put the d by dz on the inside. Anybody know why that's justified?
Isn't it because if you derive each part from the outside, it's just gonna like FOIL out, versus when you do it on the inside, it's also
but it's an infinite. You're treating it like a polynomial, but when you do that, right, you're saying, oh, well, I've got this polynomial, I could go term by term. So that's justified for polynomials. What justifies the fact I'm doing it for a power series? That's not part of the homework exercise. I'm just curious, like, if anybody knows why you can do that. It's because the power series z to the n over n factorial has an infinite radius of convergence. It's a convergent power series where it doesn't matter what z is. So if you did the ratio test on this thing, you would find that the radius of convergence is infinity. Okay. So this is the same thing as switching the integral and the derivative, right? The fact that the integral existed meant we could put the derivative inside. Same thing here. The fact that the series converges lets me stick that d by dz on the inside. Then, I didn't catch who made the suggestion, but you just take the derivative. Now, a thing that you would not want to do is cancel the n and the n factorial from here. And the reason you wouldn't want to do that is you would first want to make the observation that this is equal to the sum from n equals 1 to infinity of n z to the n minus 1 over n factorial. And if you just cancel away the n's, it's not clear where the n equals 0 term went. So what I've done is I said, well, if I put 0 into n times z to the n minus 1 over n factorial, I get 0 over 1, which is 0. So why bother including that term? I can just toss it. That make sense? All I've done here was I noticed that if I put in n equals 0, I get all of this is equal to 0. So I can start the series at 1 if I feel like. And now I can cancel the terms out. And now I can just index shift back to the original series. That's it. Here, if you like, you could set t is equal to n-1, say. Or, and a lot of people did it this way, you could write down that really what you're doing is d by dz of 1 plus z squared over 2 factorial plus z to the third over 3 factorial dot, 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 which is equal to 0 plus 1 plus 2 times z squared over 2 plus 3 times z, this is to z, 3 times z squared over 3 factorial, which is just 1 plus z squared over 2 plus z to the third over 3 factorial, which is obviously the original series. I mean, what you started with is what you ended with. So if you don't like the sigma notation for it, you could just expand it out and apply the derivative. And what you start with is obviously what you end with. And that also shows the rule is true. And now what you can conclude from this is that if e to the z is defined by that power series, then it must be the case that d by dz of e to the z is e to the z, because we've proved that that's true. You can't use what you're trying to prove. Is that helpful?
Yeah, that makes sense.
Okay. Now, for part A, or sorry, part A, problem 1, when you have something like g of t is equal to the sine of 3t times the cosine of 5t. Almost everybody on the quiz did this step correctly, which is they noticed that you could replace the sine of 3t with e to the 3it minus e to the minus 3it over 2I, and e to the 5it plus e to the minus 5it over 2. Where a lot of people fell down on this question was then they didn't multiply through. You can't just do this and say it's it's the Fourier series, because it's not. I haven't multiplied this out into individual terms of complex exponentials that are added together. If you multiply all this out, what you get is 1 over 4i times, I think, what, e to the 8it, and then there's going to be a minus e to the minus 8it, and an e to the minus 2it, and a minus e to the 2it.
So now you want to talk to me.
That was my roommate. Sorry about that.
It's all right, man. So I got screaming kids and a yowling cat in the background. So it's just I think the way it is right now. Minus 8it plus 4i e to the minus 2it minus 1 over 4i e to the 2it. This is the Fourier series for that function. So it's all multiplied out. I can actually look now at these terms and identify, okay, I have an n equals 8 term, not n equals 8, because not really a Fourier series in the way that with the n's that we're thinking about it. But I can look at the harmonics that are present and say that's a Fourier series. And the harmonics that are represented here go with certain frequencies. So the frequency of this one is related to its period. And so what we do is we're going to identify the periods of each individual term. The period of this function is equal to 2 pi, because that's the period of the basic e to the I theta function, divided by 8, which is pi over 4. There's a mistake a lot of people made, to work in frequency instead of period. When we're looking for period, we have to work in period, which is the reciprocal of the frequency of the individual terms. The frequency of these terms, or sorry, the period of these terms is 2 pi over 2, which is pi. So I have two terms that have period pi over 4 and two terms that have period pi. What's their combined period?
Just
Your
pi?
audio is absolute horseshit.
It's pi. Because, yeah, the 8it terms have to do themselves 4 times before they land where the e to the 2it has started over again. Or if you like, 4 times pi over 4 is equal to 1 times pi. And so the least common, or, a common multiple of pi over 4 and pi is 1. It actually turns out to be the least common multiple. So the combined period is pi. Because I could solve the equation k times pi over 4 is equal to L times pi. And that's how you find that. Does that make sense?
Yeah.
All right. Now, if I ask you, I should say, when I ask you question 1 on the exam, I expect when I look at a Fourier series to see the entire series written out so I can identify all the coefficients of the series. And these product problems are useful because they separate people that understand you have to multiply this out to figure out what the frequencies that are present are, from people that are just willing to do the substitution and then use the 5s and the 3s. And the problem is the 5s and the 3s do not appear in the Fourier series, right? So when I ask you this question or something very much like it again on the exam, then you'll know, do the substitution and then multiply everything out so you can identify which actual frequencies are present, because otherwise you can't find the period. There's no way to do it otherwise. Is that all right? I can go a little bit longer today, so I'm not in a hurry to get out of here if people have more questions they want to ask. Okay, so quiz 4. Especially since I spent the first 10 minutes answering the wrong question. Okay. So these are also like really good exam questions, or questions like these. So if I want you to show me that e to the 2 pi I n t over capital T, that this family of functions is orthogonal with the inner product f dot with g is equal to the integral from 0 to t of f complex conjugate of g dt. What I'm asking you to show is that any two of these that I stick into that integral, when I do the integration, I get 0. So let's do that.
Can you say that again? You said if you plug in either f or g, it turns out 0.
Okay, so what it means for functions to be perpendicular to each other, so f is orthogonal to g, means that f dot g, or the inner product of f and g, is 0, right? As long as f and g, I mean, that's what it means to be orthogonal, is that's a 0 integral.
Yeah, that makes, I remember that from before.
Okay, so what we're being asked to do here is pick two different of these exponentials, right? So I'm going to do a dot product of e to the minus 2 pi, it's not minus, e to the 2 pi I n t over t, and I'm going to dot it with e to the 2 pi I n, I don't know, how about t hat over, not t hat, with a different n, so it's m. And let's just suppose further that n and m are not equal to each other, because a function can't be orthogonal to itself. So you do that dot product. And what we're going to show, hopefully, is that this is equal to 0. So how do you do that? Well, you take the integral from 0 to t of e to the 2 pi I n t over t. But then because in the dot product, we're taking a complex conjugation of the second entry. So whatever is here ends up with a conjugate on top of it. That means that this isn't going to be 2 pi I mt. It's going to be minus 2 pi I mt over t. And algebraically, that simplifies into the integral from 0 to t of e to the 2 pi I n minus mt over t.
Where did that t hat go? Are we just ignoring t hat now?
Well, I was wrong. I don't want t hat. I want n and m to be the things that, right? Because this family is actually indexed over different values of n. So n goes from minus infinity. N goes from minus infinity to infinity.
Yeah.
Okay.
Okay. So I have chosen two different values of index to make sure that they don't match each other. Because if they did match, I'd get e to the 0, and that actually does have an integral. Okay, now you do this, and what you end up with is this nasty looking thing, 1 over 2 pi I n minus m, and then because it was over t, there's a t on top, times the integral, not integral, times e to the 2 pi I n minus m t over t, evaluated from 0 to capital T. That's just the regular old, like, integrating a complex exponential. When you do that, you're going to get this. When you put in the t, the big T here cancels this t right here, and you get e to the 2 pi I times n minus m. You put in a 0 for little t, and you get e to the 0, which is 1. What's this equal to? E to the 2 pi I times some integer. Well, what's e to the 2 pi I? I saw somebody unmute. What's e to the 2 pi I?
1.
Yep. Why?
Because it's like you're going around the unit circle.
Yep. It's just you're starting at 0 and going around 1 time, and then you're landing back where you started. So if I took e to the 2 pi I and I raised it to the n minus m power, well, e to the 2 pi I n minus m is just e to the 2 pi I to the n minus m, which is 1 to the n minus m, which is 1. So this is a 1, and this is a 1. So e to the 2 pi I times an integer is always just 1, because it just means go around the unit circle n minus m times. So this whole thing is just 0, because 1 minus 1 is nothing. And that is all it takes now. What you've just shown me is that e to the 2 pi I n t over t is perpendicular to e to the 2 pi I m t over t, because their dot product was nothing.
That makes sense. Thank you.
Cool. All right, now as far as the square wave function goes, this is actually another really useful one, because it's a direct application of the theory that ends up with a pretty nice formula. We have this function that comes in and it hits 1/2, and then it jumps up to 1, and then it does 1, and then it falls back down again. Is that the one we're doing? Oh no, sorry, we're not doing the rectangle. We're doing its shift that looks like this. -1, sorry. Like that. And then we're making it periodic, right? So we're thinking about this thing as being like, make sense?
Mhm.
Okay, so this is 0, this is 1/2, and this is 1. Okay, so let's do its Fourier coefficients. So first off, I want somebody to tell me, just looking at this function, what f hat of 0 is. What's the 0th Fourier coefficient of this function? Anybody can eyeball it off just the graph?
0.
Why?
Because that's the average value.
Exactly.
0 to 1.
So that's the average value of the function.
I'm doing pretty good. How you doing today?
Okay. So because this function spends an equal amount of time above and below the axis, I mean, you could think about this as having area positive 1/2 and this having area minus 1/2. When those cancel, right? So the average value of the function is nothing. So what about f hat of n? So the nth Fourier coefficient is the integral from 0 to 1 of f e to the minus 2 pi I n t dt. That's just the definition of a Fourier coefficient. But the definition of f changes between 0 and 1/2 and 1/2 and 1. So we rewrite this as the integral from 0 to 1/2 of 1, because that's the definition of f on the first chunk, e to the minus 2 pi I n t. And then we have an integral from 1/2 to 1 of -1 times e to the minus 2 pi I n t. At this point, I just integrate, plug in. So you get like -1 over minus 2 pi I n e to the minus 2 pi I n t evaluated from 0 to 1/2, plus the integral from 1/2 to 1 of, sorry, that minus comes down, positive 1 over 2 pi I n e to the minus 2 pi I n t evaluated from 1/2 to 1. What you're going to get when you plug in the limits of integration here is, so there's actually something else we're going to have to deal with. So I'm just going to do it. 2 pi I n, and then we have an e to the minus pi I n t minus 1. I know I forgot a negative. And then e to the minus 2 pi I n minus e to the minus pi I n. Why does it matter if n is even or odd? Look at this formula.
Because like if even, or you have the negative pi in and negative 2 pi in, so when you plug in even and odd, one is going to be -1, the pi in, and the 2 pi in is always going to be +1.
That's right. This is always an e to the 2 pi I to some power, which is just 1. This thing will change its behavior depending on if n is even or odd, because e to the I pi is -1. E to the I pi is -1. Bonus points if you remember that that's called Euler's identity. Okay. And so if n is even, then this number right here is a +1, and 1 minus 1 is 0. And this number is always 1 because e to the 2 pi in is always 1 because it's always even. But this number will also be a 1 if n is even, which is also 0. So when n is even, all of those exponentials just disappear. Nothing is left, and you get 0 out. Does that make sense?
So does that mean we get 0 plus 0 equals 0?
Yeah. I mean, 1 minus 1 is 0. 1 minus 1 is 0. And if you look at the formula we're supposed to show, the nth coefficients are supposed to be 0 when n is even. So you expect everything to cancel in the case when n is even. In the case where n is odd, you get something different. Because in the n is odd case, you get 1 over minus 2 pi in. But now, if n is an odd number, this is a -1. This one is always +1. And now we're going to subtract off another -1, because what happens is in the odd case, this term and this term become -1s instead of +1s. You look skeptical, Connor.
I just didn't know how to do it. No, that makes sense. I can't see how it like kind of worked out.
Yeah, so I mean, so that's gonna so the big deal with these type of questions is that it's always going to be the case that when you get these exponentials, you have to check and see if the even and odd terms are different, because if I ever write down e to the 2 pi, if I ever write down e to the 2 pi I anything, that's always equal to 1. And if I ever write down e to the pi I anything, that's going to change its behavior on if this is even or odd. And that's what the distinction is, why we have to watch for that when you do these formulas. So whenever e to the pi i's show up, you're always going to have an even odd separation.
Okay, so I should just always like kind of have that as like a mental like note.
Yeah, and if I'm going to ask you a question, it's going to look a hell of a lot like this one anyway. It's going to be the same sort of model where I give you some function to do. It's going to fall into an equation like this where either nothing disappears because it's all e to the 2 pi i's, or there'll be two cases to consider where you have e to the pi i's and, you know, and the e to the pi i's meaning you need to split n's from even to odd. So,
okay.
Yeah, so I think in this case you end up with 1 over pi in when you add them together, which is the same as minus I over pi n. Oh, there's an extra 2.
Wouldn't it be 2? Yeah.
Yeah. So there's an extra 2. Yep. Yeah, because there's a 2 that comes out of this, another 2 that comes from right here. Everybody good with that? Sorry, Teo.
Oh no, I had a quick question, not relating.
Okay, please.
So I guess this is a class question. I don't know if this is in the calendar, but is the midterm this test that we're taking this week, or?
So there's two midterm gets thrown around in these quarter system schools kind of oddly because everyone just uses them to mean exams, right? So this is not a midterm in the sense that it's the thing that evaluates your midterm grade. It's the second exam. And so, yeah, the sloppy way of saying that is 2 midterms, right? So there'll be 2. So there's 2 exams basically to build out the first 2 units of the course. And so all this next one is going to cover is just the FOIA stuff that we've talked about.
So it's not cumulative then?
This test is not cumulative. This test this test only covers the stuff from quiz 3 and quiz 4. And then maybe there'll be one question about the like, like applying the Fourier transform to something really simple, right?
Okay.
But it's just covering, like, if it was on quiz 3 and quiz 4, then it's fair game to be on here. So like the emphasis is going to be on Fourier coefficients, right? But quiz 1 and quiz 2 stuff we're not going to come back to until the final. And then we're going to switch gears again. So like in an ideal world, if there was more time, I'd actually give 3 midterms, because I don't like having testing people on the final on stuff that they haven't seen on a midterm before. But because this class is so compressed because of how much content there is, I just can't make room for another test. But the last part of the class is actually going to be way more computational, because it's about the Laplace transform. And so once we've built up all this stuff about Fourier series, we're going to go back to solving differential equations with a different transform. So the Fourier transform, I think I pointed out earlier, has the problem that you have these Fs that you have to have two-sided behavior where they go down to nothing very quickly. And the Fourier transform can be used to solve differential equations, but it's actually pretty difficult. So we're going to do a different transform that, instead of integrating from minus infinity to infinity, integrates from 0 to infinity. And it gets used all the time in studying systems, circuits and systems of differential equations. And that's called the Laplace transform. But it's going to be another kind of one of these integral transform ideas. It's just that we're going to be aiming at solving differential equations with it. So yeah, I mean, this class is relentless. It's actually quite difficult to teach because there's just so much. I'm already having to pick and choose what I'm showing you guys. And I have to hit the content that your engineering professors expect you to have seen. So there's stuff I'd really want to do that I can't. There's just no time. Like, you could do an entire year on Fourier series. Just what we've done just for the last 4 weeks could cover a year if you did it in full detail. And if you guys, did anybody in here have to take signals or control?
I'm taking that right now, and we're going over Laplace. So I was actually going to ask you a question about it, but
Oh no! Well, why don't you stick around until I'm done, and you feel free to ask me a question.
Okay.
Laplace transform is another good transform.
I just have a quick question. Are you gonna potentially post practice problems before
that is going up today? Yep.
Okay.
Just like it's going to be just like the last one, where the exam questions are going to basically look exactly like. I mean, I think last time I basically just asked you guys quiz questions again, mostly, right? So I'm going to give you some practice problems to work on. You should expect that the issues that I'm hitting in the homework, the really technical stuff, is stuff that I think is important to have seen, like wrestling with, like, the restrictions on F and the Fourier transform. But I can't ask you that on a 50-minute test, right? I could feasibly ask you to do a Laplace or a Fourier transform of like a baby function, but I can't ask you anything technical or proof oriented or long, unless it's one like this one right here, right? To show that these functions were orthogonal to each other. This is a nice question. I guess that's, maybe I'm letting the cat out of the bag a little bit, but it's a nice question, right? I mean, these are questions that are the sort of core ideas, but they're also doable. So just like last time, I got to give you doable questions. So
we're taking the midterm was pushed back to Monday and Tuesday, correct?
Yeah, so I was gonna see if I mean, I could open it earlier, I guess, if people really want to do math on the weekend. Most people don't, but what I was thinking was I would open it up on Monday morning and then have an office hour. So if people want to stop by or they were worried, they could come hang out on Monday and ask me questions about the practice test. I like to give practice tests, and people have a chance to come in and actually ask about what it is that they've been asked to do.
Mm-hmm.
So I'm thinking Monday and Tuesday. I'm open to feedback on that, but since the last test got pushed to Monday, it seems like it's only fair to do this one too, instead of crushing it in. I mean, I could give it tomorrow, but I haven't given you any prep. So
yeah, Monday sounds good. Monday or Tuesday.
And then what else did I want to say?
Also, one thing. Also, do you have like a solution like guide to the homeworks? Or
so yeah, all the homework exercises in the first section already have exercises, the answers posted. All of it. So that's like if you go on the OneNote folder for the class, I don't know if you've been in there yet.
Oh, I didn't know that existed.
Yeah, so if you go on the home page, the last link or second to last link when you land on the Canvas page says Linear Analysis 2 Notebook. Inside there, I have solutions to the first. Yeah, so there's a tab that says Homework Solutions. So the first 6 homework assignments have solutions written out there, and then I'll add solutions for the next 3 today and tomorrow. So those will also all be there.
And those are for like the quizzes, like 3 and 4 homeworks, for example.
Yeah. So the stuff I have, so that, yeah, so the quiz 3 and quiz 4 homeworks, those will be posted today.
Fantastic. All
And
right.
also, and then this homework assignment 2, I will also post prior to the exam so that people have that to pull from as well. Like,
Cool.
the reason I don't post those early because I know that I get some pushback from students about this who like to look at solutions and then guide their thinking based on the solutions that they see. But I think it's important to try to struggle with these questions first, as irritating as it is, and as professor teacher is to say, oh, you get all the value out of struggling with the questions. I think you do. So I like posting the solutions. I don't like posting them until people have a chance to actually try the questions. So
For sure.
so yeah, you should expect all the homework solutions to be up sometime today.
Cool.
And practice questions for the the midterm, and then I'll post another office hour for Monday. And yeah, anything else like that I can answer, I'm happy to. So
will the midterm practice problems have solutions as well?
Yeah, I think I did that last time. I mean, I did that. So yeah, that's I want people to go in with a full set of. I mean, this is an open note class, right? I want people. I'm not trying to restrict that. I want people to come in with a full set of materials. So yeah,
cool.
Yeah, it turns out this is it's a lot of work.
There's a lot of material.
I mean, I'm like, this is pretty much all I do is this class. It's all day. It's just thinking about this class and writing stuff for this class. So yeah, it's like really fun stuff, but dude, it's not easy.
It's dense.
Yeah. All right. So with that, if I have, I guess I have more questions about email and stuff, you could do that. If you want to check out the solutions that I'll be posting later today on the homework, do that. You should expect, if you're going to see something on an exam, it's going to be something more on the order of questions 1, 2, and 3 than question 4. Question 4 is important, but it's not the sort of thing that I can feasibly ask on a test. And other than that, study your quiz 3 and 4. I'll have solutions up when I can. And Teo, if you're still here, stick around and feel free to ask me about the Laplace transform if you got time.
Thank you.
Yep.
Thank you.
Thank you.
What's up?
Yeah. So I think it would be easy. I guess I could show you